Okay, good. All right, thank you, everybody, and especially to the organizers for putting this together. Today, instead of talking about one single story that's more coherent, I thought maybe I would just put a few of my recent works together that I think would be interesting to the audience. I was hearing a bunch of previous talks. Okay. So my name is Yuxuan Wang from University of Florida. Today I'll be talking about a few things I've been working on regarding pair density waves. Specifically, it's going to be composed of two parts. In the first part, I'll be talking about the Higgs mode of the pair density wave, namely the amplitude fluctuation, and whether or not and how you can detect them in Raman spectroscopy. In the second part, I'll be leveraging the properties of a pair density wave and give you a microscopic mechanism that can give rise to a charge-4e superconductivity. So in this sense, the second part will be more related to what Jian just talked about. So I'll start with some basic introduction about pair density waves. Usually for an audience of experts, I don't have to spend too much time about it, but so far I may be the first one focusing on pair density wave in this workshop so far. Okay, so what is pair density wave? Well, it's basically a superconducting order parameter that also oscillates in space. And a primitive pair density wave actually has zero average over space, but it can oscillate in space. And if you do a Fourier transform, it's composed of two order parameters, one of them carrying a momentum plus q, the other carrying momentum minus q. Right. So in recent years, there has been a surgence of interest in pair density waves. It has been recently proposed to be a concrete part of the Couperin phase diagram, namely considering fluctuating pair density waves explains a lot of the features in the pseudogap region of Couperin, especially the lanthanum-based Couperins. So this is in the phase diagram in the whole dope region around the famous or infamous 1/8 anomaly, where you have a lot of different intertwined orders. You either have charge order, and upon further lowering temperature, you have spin order, and then there's also ultimately there's also in-plane coherent superconductivity, and then finally at lowest temperature you have a fully three-dimensional superconductivity. Right? Using the principle of Occam's razor, this perhaps we argue that it's simplest to propose there is a pair density wave order whose vestigial orders can naturally explain all these phenomena. Okay, and also recent years there has been a lot of experimental evidence of pair density waves, or more accurately, I think, spatially modulated superconductivity has been observed in a lot of correlated materials, including these materials, but definitely not limited to these materials. From a symmetry point of view, as I briefly already talked about, it breaks multiple symmetries. Just as any superconducting order parameter, it breaks the U1 symmetry, but also it breaks translation symmetry, right? So if I only care about symmetry, then you may think, okay, this is just pretty similar to a coexistence states between superconductivity and charge density wave order, which breaks exactly these two symmetries, right? So indeed, these are perhaps the more mundane scenarios where you have superconductivity inside the CDW phase. This is TiFe2 and niobium diselenide, which just features the coexistence between CDW and SC. So if I only care about symmetry, you may say, okay, this is also just a spatially modulated superconductivity, right? I should also say, perhaps the first idea of a pair density wave is the well-known FFLO state, which occurs through an external Zeeman field that forces your electrons to pair with a finite momentum, right? So I guess the question we're going to ask is, how exactly, is the pair density wave state we're talking about distinct from these, relatively more well understood scenarios, right? So we can say from a theoretical point of view, right, the distinction is that for paired density wave, it's coming from some strongly correlated mechanism that doesn't require a Zeeman field, unlike the FFLO state. And also, it doesn't require any fine-tuning of order parameters to land you on a special region on the phase diagram. It's a single mechanism that can naturally break both of these symmetries, right? But experimentally, an equally important question is, how can we really tell is there any sharp feature for a paired density wave state we're talking about that truly composed of delta plus Q and delta minus Q that distinguishes with more mundane forms of modulated superconductivity than maybe just due to superconductivity and CDW, right? So this is a question we're going to ask, and the focus our focus to resolve this problem is by looking at the collective modes. Okay, so by collective mode, let me bring you back to the collective mode of a regular, spatially uniform superconductor. Right, this is the classical Mexican half potential. When you are at a temperature smaller than Tc, then your free energy has this form, and then the ground state is any point in this trench, right? So now if you consider the fluctuation of the order parameter, naturally there's two directions of fluctuation. You can either fluctuate tangentially along the trench, that causes very low energy, and also you can fluctuate in the longitudinal direction. These are known using the field theory language as either a Nambu-Goldstone mode or a Higgs mode. Right? In field theory, the Nambu-Goldstone mode is gapless, has zero energy. It disperses linearly with momentum. However, we also know due to a well-known Anderson-Higgs mechanism, once the gauge field or the Coulomb potential is included, actually the Goldstone mode is no longer low energy. It actually got elevated all the way to the plasma frequency. While the Higgs mode itself, if you compute its energy, is exactly twice the gap, right? However, this Higgs mode lands right in the region of the quasi-particle continuum, which starts also exactly at 2 delta. So yes, it has a energy at 2 delta, but because it overlaps with quasi-particle excitations, then you can actually scatter into quasi-particles, giving it a finite lifetime effect. So in terms of spectral cost, spectroscopy, the width of this peak will be broadened. Okay? Yes.
Just a comment. So for the Higgs mode, what you call amplitude mode, its structure depends on whether you consider relativistic or non-relativistic theory.
Right.
So which one are you? You're assuming that you're in a system which is non-relativistic.
Right.
Particle hole symmetry.
Right. Because so far, right now, I'm just looking at Q equal to 0. Right. So I think whether it's relativistic or non-relativistic may be relevant for the dispersion.
Well, not really. I just mean in non-relativistic theory, the amplitude mode is a canonically conjugate to the phase.
Right.
And so it's not really a separate mode, it's just a momentum conjugate to the phase. Well, in the relativistic theory, it's an independent mode.
Precisely, yeah. So you need exact particle hole symmetry for it to exist.
If I don't have exact particle hole symmetry, what happens?
Then it mixes with the phase mode.
It mixes with space mode.
Yeah, it just, it's like momentum.
I did
Right.
this in
Okay. Yeah.
And it's not Higgs. It's a basic rules.
Okay. Higgs mode. But in here, you see the amplitude modes. They're both damped since their energy are all within the continuum, right? However, in order to make it sharp, this is actually Chandra's early work in 1982 with Peter Littlewood. The Higgs mode may become undamped by coupling with another mode. So because of level repulsion, you can actually push the energy of the Higgs mode down from 2 delta so that it becomes sharp and then becomes detectable in Raman spectroscopy.
May I make a tiny remark?
Yes.
Higgs mode has no dipole moment, no quadrupole moment, no spin.
Right.
So it is undetectable
gonna
unless
talk about that,
something
yeah.
special happens.
Yeah. yeah, here in your case, you couple it with CDW phonon, right? All right. So if I, bring our attention back to the context of pair density waves, we do have two different modes, right? Because we have two different order parameters, delta Q and delta minus Q, which also breaks translation symbols. So now, if I don't consider their pairing, just by counting the modes, the amplitude sector, there are already two different modes, either from the amplitude fluctuation of delta plus Q, the other from minus Q, right? However, naturally, in a theory, they will be coupling to each other, right? So their coupling can be described actually within the framework of Ginzburg-Landau. What I have is write down a free energy. So the first three terms is just separate free energy for delta plus Q and delta minus Q. In the last part, I have a coupling between delta plus Q and delta minus Q. Okay? So what I can do is to expand this free energy around its local minimum. Then what I get is something like this. So where A is the fluctuation and delta Q is the equilibrium value. Now you see this last term, gamma, becomes an effective level repulsion between these two Higgs modes. Okay? So as a direct consequence, you can evaluate the sign of gamma from integrating out the fermions. It turns out to be positive. Then what happens is that the two Higgs modes, now they're split in energy, right? Just diagonalizing a 2x2 matrix. Their relative, because of the repulsion, right? Their relative amplitude mode becomes lower in energy, and the positive mode becomes higher in energy. Okay? So this one actually now, turn right, it actually now carries a dipole moment because it is odd under inversion. So, now you can see that this A minus mode will have an energy smaller than 2 delta. So the natural question is, maybe we can observe a sharp Higgs mode and a peak in Raman. Okay? However, that immediately comes with two caveats. Actually, it's not entirely ideal. The first caveat is that if you look at the symmetry of this relative mode, it's actually odd under inversion. So which means it actually doesn't couple to Raman. Raman couples to electron quadruples, right? So it may be detectable through direct process, but not in Raman. Second, this 2 delta threshold for damping is actually not very sharp for pair density wave state. The reason is that the pair density wave state, even though you have a gap, it does not gap out the entirety of the Fermi surface. So while you do have relatively sharper feature if your energy is below 2 delta Q, but it's not exactly sharp. So it's not a very sharp
Excuse me,
feature.
why do you think that fermionic spectrum in PDW is gapless?
What I mean is that if you think about superconductivity, right, it gaps out every point on the Fermi surface because it involves plus K and minus K. But for PDW, it involves plus K and minus K plus Q. So it actually does not, it only gaps out the hotspot regions on the Fermi surface.
But here you assume, here you are assuming a certain microscopic mechanism for PDW.
No, I'm
Like
just thinking
F
about
of O.
kinematics, right? So in order for a PDW order parameter to decay into two low energy fermions, right, to gap out, then just diagonalizing a VDG Hamiltonian per se. Right. I'm talking about mean field theory, just delta Q, right? It doesn't have anything to do with mechanism of this. So if you just diagonalize this Hamiltonian, you will get a mess. Of course, your Brillouin zone will get folded, and then you have a lot of gapless regions. Okay. All right, so what we think is really fundamentally qualitatively different is if I consider a state that has coexistence between pair density wave and uniform superconductivity. So it's well motivated because many candidate materials for pair density wave, they also have a uniform superconductivity component. For example, this is LBCO, where if you lower the temperature farther enough, you will also have a uniform component. Right? Usually, when we think about coexistence between pair density wave and uniform component, we tend to think about a picture like this. There's some uniform background, and on the same background, the order parameter fluctuates back and up and down. However, we found it's not necessarily always the case because if you do a free energy analysis, it's allowed to have a term that looks like this. It has a delta 0 square and delta q times delta minus q. It preserves both the U1 symmetry and the translation symmetry. Now, if I assume, actually, I can verify if beta is positive, then in a ground state, what you have is that it will prefer to have a relative phase difference between the uniform superconductivity and the pair density wave. So in real space, this actually has the same symmetry as the staggered current that actually breaks time reversal this way. And in this cartoon, I would have to draw another imaginary axis. And it turns out when beta is positive, this kind of configuration is more energetically advantageous. Okay? So what we're suggesting here is already at a thermodynamical level, pair density wave plus superconductivity plus uniform superconductivity is already a very fundamentally different phase than CDW plus superconductivity, because it generically would break time reversal symmetry. Right? Symmetry-wise, it's not exactly the same necessarily. Also, this same term I sketched before actually fundamentally also alters the hierarchy of the collective mode. Actually, you can show, irrespective of the sign of beta, you can always make this term negative, right? And then if I do this expansion for the collective mode, what I have is, aside from the previous level repulsion term, here I would additionally have a level attraction between them. Okay? So this is a Ginzburg-Landau expansion. Within the realm of validity of the Ginzburg-Landau theory, you can show actually this level attraction always wins over the level repulsion. So what I'm saying is, when I have superconducting, uniform superconductivity as an element in a theory, these two modes actually alters role. Okay? So actually now this A plus mode becomes much lower in energy. And another, so also A plus mode is even under parity. So it actually couples to Raman vertex in the A1G channel, and then at least it can be detected. What is even better now, because I have a uniform component for my superconductivity, the fermions are fully gapped. So now this threshold of 2 delta 0 becomes a sharp decaying thread. So when we actually calculated the Raman spectrum, actually we indeed get a very, very sharp peak at low frequency, and we verified exactly corresponds to this collective mode between the synchronous mode between delta plus q and delta minus q.
Can I ask
Yes.
so, I mean, the point, your earlier point of this coupling of uniform and the pair density wave, you don't have the CDW at Q. You have it at 2Q, but not at Q. Is
Right.
that
Yeah.
idea?
Actually, it's a current density wave at plus q in that case.
Right.
Because it's
I
a
see.
relative. Right. So if you do STM, you will not see the 1Q peak.
Okay, good,
Right.
okay.
Yeah. Other question? Yes.
So another question. So
Mhm.
if there would be a CDW,
Mhm.
and if you assume that CDW is the primary order,
Mhm.
then there would be also a cubic term that connects the pair density wave to the charge density wave
Right.
and your homogeneous term.
Right.
That I guess would dominate this tendency to break time reversal symmetry because it prefers a pi phase.
That's true.
Right.
Yeah. 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 So this goes along the same line as I was saying. There is a fundamental difference between pair density wave superconductivity and charge density wave plus other things, right? Because this time reversal symmetry actually indicates a thermodynamic phase that is separate from the other scenario. Okay. So. All right. There are further questions about the first part?
If I could ask a question,
Yes.
for this particular case, there were like also many works on how to detect like for mode mixing in like S plus IS, S plus ID superconductors. You also you expand near ground states all kinds of modes mixed in various ways.
Right.
And so like if you consider your system versus those systems, like what would be your kind of hallmark signature that is not like if you see like some soft.
Right. This is something we found rather remarkable, to be honest, because we solve it analytically. The best way you can do is just to do the Ginzburg-Landau theory, and then you wave your hand, okay, saying it's below the decaying threshold. However, numerically, when we're computing this Raman vertex, we found in a wide range of parameters of the ratio of delta 0 and delta Q, actually you always get a very, very sharp peak in the Raman channel. While also try it for other phases, not necessarily S plus IS state, but
Yeah, I mean, like many other like
CDW and superconductivity, then you do have some sharp-ish state, but it's never as sharp as this. It's something we need to still understand, because in that limit we need to go beyond Ginsburg lambda and solve it at 0 temperature. We could only do it numerically at this point. Yes.
How did you manage to ensure that delta to power 4 terms are getting bigger than double delta?
You mean what? Which one?
Well,
These
whatever
two?
is written here is delta to power 4.
Right.
But the gap itself is delta. And somehow you say that those shifts can more or less overcome the gap itself.
More or less.
I would assume that those shifts are just tiny, 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 tiny.
Right. Well, the shift is proportional to delta.
Well, but I
zero
look at the
squared.
picture. The picture
Right.
looks like it's a huge separation of scales.
Right. So the only way you can justify the Ginsburg lambda expansion is when delta naught is much larger than delta Q and delta minus Q. So otherwise, the Ginsburg lambda expansion is not trustworthy. I am helpless. I can only do numerics, and turns out to be magically still robust. Right. It's something we don't understand fully. But within the theory, we do know, in order for this procedure to be correct and well controlled, delta naught has to be much larger than the other term. Because otherwise your Ginsburg lambda expansion is not correct. Just like in a regular Ginsburg lambda expansion, you need delta over T to be much smaller than 1. In here, you need delta Q minus delta 0 to be much smaller than 1.
I think, Yuxuan, the question is basically on this graph, what is the scale of delta naught?
What is the scale of delta?
Yes,
This
on
one?
on the one where you show the Raman spectrum.
Yes.
So where is the delta naught? What are the energy scales of the deltas on this?
I
Because
think in
it's
this
a very
case they're
soft mode,
comparable.
but
Everything
it
is
should be well
comparable.
below 2 delta then.
Yeah.
Yes, so.
Yeah. They're comparable, but this one is definitely below 2 delta. Yeah.
Okay.
Yeah. I can go to the same region that this goes, but the feature will be the same. The splitting may look different, but we still have a sharp mode. Okay. So let me go to briefly the how am I doing with time?
7 minutes?
Okay. Well. All right. So I'll be talking about charge-4e superconductivity. Now, from a bidirectional pair density wave. Okay. So we said a pair density wave state breaks both translation and U1 symmetry. And with fluctuation effects, there's no reason to expect both symmetries to be broken at the same temperature. Indeed, I can construct these vestigial orders that restores translation symmetry, because the combination has 0 momentum, right? But still breaks U1 symmetry. If you count how many charges this object carries, it carries charge 4e, right? But this is not the only way to combine it. There's other, so in this sense, we have a pair of pairs, which reducing to electrons, it has charge 4e, right? On the other hand, you can also combine like this. It's easily imaginable to have delta Q, delta minus Q individually being 0, but this combination not being 0. This object will break translation symmetry, so that will correspond to a vestigial charge density wave order parameter. So this problem has been studied in different contexts by a lot of people. It is just not a exhaustive list, of course. And in this paper, this model was studied at a phenomenological level, which ended up as a phase diagram, which shows you can either have charge 4e or CDW, or even pneumatic state in different regions, right? But the key challenge for a more microscopic level is there are so many competing vestigial orders, so it's difficult to tell under which situation charge 4e is the leading order. And our goal is to find maybe whether or not there is a microscopic mechanism for charge of 4e as the leading instability. This is a key challenge. The way we tackle this problem is to consider the same pair density wave state, but now the bidirectional one has both plus q and plus p, so which are related by a 90-degree rotation. So we know what we're going to consider is kind of the pairing of these bosons, right? Because my pair density wave now happens at finite momentum. So it's a little bit like the fermionic pairing, because fermionic pairing also occurs at finite momentum around Fermi surface, right? You can imagine this as kind of like a Bose surface. Right? So when we're considering the analogous problem from fermions, we consider fermions interacting through exchanging bosons, right? here is kind of the dual process. We're considering the bosonic interaction by exchanging fermions. Okay? So in the former case, if you want to have a very strong fermionic interaction, we usually look for some low energy bosonic mode, which is only there for near critical system. However, in the second scenario, it's much easier because you always have low energy fermions around the Fermi surface, right? So when we're considering a particular geometric relation between the PDW momentum and the Fermi wave vector, we were able to show that these interactions are very much enhanced, and you can also directly evaluate these coefficients. We're able to show this kind of pairing interaction, where psi means the PDW order parameter, is actually much larger than other kinds of interaction. For example, this beta 2 term, if it is the leading one, it would have promoted a pneumatic order. But here we can microscopically show that this pairing interaction is actually the largest. Okay? So, but there is one huge problem here. This interaction beta I just showed you is actually repulsive, just like a repulsive fermionic interaction, right? But now we have experience in the fermionic pairing problem. We know how to solve it. All we need to do is to go to some finite angular momentum channel. So it's rather easy. It just rewrite this via an identity. It turns out to be attractive in the D-wave channel. Okay? By D-wave, I mean P and Q, they're related by 90-degree rotation. So it is actually attractive in this channel. And then it's quite similar to fermionic pairing, and it is attractive in this channel, as I said. Then, of course, this is just showed you have attraction here, right? In order to describe the phase transition, we still need to understand the dynamics of the bosons, right? So we write down the free energy, including the spatial fluctuations. And we know at low temperature, assume we're in a two-dimensional system, the theory is actually dominated by phase fluctuations and the dynamics of the vortices, of the topological defects. Right? So before we analyze that, we know I can rewrite my order parameter in terms of the theta and phi phases. Right? If we order in a common phase, then it leads to a charge-4e superconductivity. If we order in the relative phase, we end up with the charge density wave phase. Okay? Here, interestingly, this beta term, as we just said, that is the pairing term, it kind of logs the phase between theta and theta bar. So what you end up having is effectively you have enhanced stiffness, because the stiffness term for both theta and theta bar, they get added up together. Right? So the upshot is that if I rewrite it as into a phase fluctuation only model, in the theta sector, kappa 1 and kappa 2, they actually add up. Right? In general, kappa 1 and kappa 2 are not equal to each other because symmetry does not require them to be equal. However, in this phi sector, they actually there's no coupling. Effectively, what you have for the effective stiffness is the geometric mean between kappa 1 and kappa 2. Okay? So at this level, it may appear that theta and phi bar, they're independent variables. However, as I said, the phase transition ultimately is driven by topological defects. If you consider the topological defects, you realize these variables are not independent, because when delta theta winds by pi, in this case it's a half vortex, fractional vortex, delta phi is forced to also wind by delta plus minus pi. So in real space, this is a half vortex bound by dislocation. You can consider multiplicity of this defect. You can get a full vortex or double dislocation. So to analyze the phase transition in 2D, I need to understand whether or not and how these topological defects proliferate. Okay. Transition occurs by binding and proliferation of these defects. And one interesting mathematical fact you can immediately observe is that on one term, for theta, you have an algebraic mean times some number. On the other one, you have a geometric mean. Right? So this obviously is always larger than the geometric mean. So this tells us theta tends to get order first as opposed to phi. Okay? Especially when kappa 1 and kappa 2 are very different. Right? So by actually doing the problem, by dualizing it into a sine Gordon model, we were able to obtain this phase diagram, you can see depending on the ratio of kappa 1 and kappa 2, you can actually have an intermediate phase where you first enter a charge-4e state before entering a pair density wave state. Okay? So actually there's no region in the phase diagram that has a charge density wave phase. Okay? There is actually intuitive way of understanding it. Right here we're saying basically the anisotropy of the PDW susceptibility around the around the wave vector actually helps the charge-4e order. One way to understand it is basically like thinking about this in the extreme limit, then basically these bosons becomes a Bose surface, just like the Fermi surface. And we know if I have a Fermi surface, right, I can consider the competition between charge density wave and superconductivity. Obviously, superconductivity wins because it comes automatically with nesting. But for CDW, in general, it loses because of lack of nesting. It's actually the same mechanism, but recast in a very different language here. Okay, with that, I come to my conclusion. We argue that in the coexistence state between superconductivity and pair density wave, there is a sharp Raman active Higgs mode, which also tend to break time result symmetry. And lastly, I present the microscopic theory that leads to a D-wave charge-4e superconductivity from the anisotropic pair density wave stiffness. With that, I would like to thank you for your attention.
Okay, we have some